So thank you for putting together this great conference. I endorse the outcome, but disavow that I materially contributed to the success of this conference. And I guess I also have the opportunity to welcome you here, et cetera, as a co-organizer, but we'll go over that. I guess, Jamir did get me to be on the committee that decides on which poster gets to present tomorrow. So if when you ask me a question, you're also associated with the poster, mention your name so that I remember to carry the favor forward for later on. Anyway, it's a pleasure to be here. So I managed to make the title fit what I declared some weeks ago, but I think the abstract is a little different. So in case you read the abstract, don't be shocked that what I'm talking about is a little different than what I promised there. So before going to my talk in earnest, I wanted to give you a little bit of my perspective on developments that have happened in the last few years and what I think would be fun and important to do in the next couple of years, especially given that the title of the conference is Quantum Designs. So I want to say that in the last 10 years or so, last decade, plus minus 2 COVID years, there have been a lot of discoveries, new discoveries on the material front. So there were topological materials discovered, for instance, three-dimensional topological insulators with surface states, gapless surface states with spin-orbit locking, and interesting magnetoelectric effects. Namely, you put an electric field on the bulk. If the surface is gapped, you get a magnetic field and vice versa. And also, many other topological materials, in particular REFAEL materials, where the bulk has a complete spin-orbit locking. So Berry curvature monopoles in the bulk appearing. Very exciting. In addition, more recently, we started seeing more RF materials showing up in transition metal decalcogenides and twisted bilayer graphenes. And these materials are very unique, of course, because you see the trend. So we're going from uniform three-dimensional materials to constructing materials layer by layer. You can really think of starting to engineer different kind of non-uniform materials. In this case, more RF materials have this unique properties of topological flattish bands at the chemical potential, as well as, as a consequence, very slow electrons. And this is one of the only systems that have electrons that are slower than phonons in the material. And I wanted to say that all these things give new opportunities for new device paradigms. Can we do something useful with that? I think we are in a unique position understanding the physics and trying to think, where can we apply this to? And then hand it off to engineers and say, look, this is a new principle for a device. All of us, well, I shouldn't project. I was, and many others, were too obsessed with Majorana fermions for too long. I think it's for a good reason. There's a Nobel Prize out there for whoever manages to prove and braid, et cetera, these Majorana fermions. But maybe one should look outside the Majorana box and think about things that are more mundane. So for instance, one thing that these new topological materials can do for you is far infrared detectors. Infrared can be detected by semiconductors, but it's contingent upon having your light have energy that's higher than the band gap of the semiconductor you're using. That's really bad if you want to detect low energy infrared or far infrared. But topological insulators, via semi metals, they have for free gapless electronic bands. And furthermore, the spin orbit coupling allows you to navigate the electrons in a way that's very different than what the currently available infrared detectors give you. So that was one direction that my group took, in particular with Felix von Oppen and Nate Linder. Some time ago, we thought, okay, if you pattern magnetically the surface topological insulator, you can get that surface to respond to circularly polarized infrared light. And in fact, that response remains strong even for infrared light that corresponds to black body radiation peak at room temperature. So even at room temperature, you can have reasonable sensitivity to 10 micrometer infrared light with such a device. And even better, you can make a vial semi-metal into a far infrared detector. And again, depending on chemical potential and temperature, you can see sensitivity of such a device that goes way up into temperature. And that's a consequence of the spin-orbit coupling. And this was work with Patrick Lee and Chris Chan and Nate. This is more of an advertisement, but you see there are opportunities to produce new devices that work very differently than the devices we have now. And in this case, allow you to detect, maybe will allow you to detect infrared light with such small frequency, where if you have more thermal means of detection, such light will be lost in the black body background of our world. What else can you do? What's next? So detectors, I talked about infrared detectors, but of course this way of thinking was taken up by other people as well. And you can try to detect spin better, entanglement, maybe dark matter. Now this sounds like science fiction, but actually groups of Roni Ilan in Tel Aviv and Catherine Zurek at Caltech have made suggestions for making dark matter detectors out of topological incidence because of the characteristics that I gave you before. What else do we need? So we need isolators and rectifiers. We're all familiar with diodes. But actually, if you think about that technology at the low temperature level, things that can go into a dilution fridge, we're really at a loss. So you can do these things with microwave. So for isolator rectifiers, things that take in a pulse, move it forward, but don't allow things to go back. For microwave radiation, the only way to do this is with interference, but that means that any rectifier is millimeters big. Can we use these new materials to produce new paradigms for rectifiers, things that break inversion symmetry at microscopic level, at lowest temperatures, things that can stick into a device that sits in a dilution fridge? That's another opportunity. And likewise, amplifiers. In high school or in the university, we learned about operational amplifiers. These amazing things that are made of transistors. They have remarkable properties. You can do negative feedback, positive feedback, isolations, all this good stuff. These things are at room temperature. We don't have anything equivalent that can go into a dilution fridge and facilitate amplification in the same level of quantum circuits that would be used for quantum computing. And the consequence of that is that readout is slow. Readout of qubits, superconducting qubits, is relatively slow. And I'm not saying that the technology that we have now is completely lacking, but it seems to me that there are opportunities for advancing such a technology based on these new materials. And actually, I will focus on this idea of amplifiers. So can we have nonlinear electromagnetic amplifiers based on these materials? Can we have amplifiers that go beyond Josephson parametric amplifiers or Josephson junction traveling wave amplifiers? Could we incorporate feedback in such materials? And I think feedback has come up yesterday quite a bit as the next frontier of in thinking about measurement-based entanglement transitions. And I'm a theorist, so I'm sure this is a very partial list of device opportunities and things that are out there that are necessary that could utilize the new developments of the last decade. Now, I understand that I may be an outlier in terms of how much solid state I was showing here, so I apologize, but I thought it's a good opportunity to also use the floor to try to give some extra motivation in this direction. But I want to concentrate for a second about amplifiers. So can we have new amplification paradigms? So I mentioned twisted bilayer graphene with slow electrons. So one thing that we think that this could be good for, and this was done with, this is currently done with Ilya Essen at Caltech and in collaboration with Eugene, who's here, but I was a little too embarrassed to put Eugene's picture when he's in the audience. So after all, I was one of my PhD advisors. So the idea is that you can sandwich twisted bilayer graphene between two semiconductors with the right chemical potential, produce an electronic inversion, and out will come terahertz phonons. So that's one way of amplifying, creating and amplifying phonons in a band of frequencies that we don't have a lot of technological control over. I think that people call the terahertz regime as the gap in the spectrum because nobody knows what to do with it. Of course, if there are terahertz experts in the audience, they would say, no, 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 our lasers are just fine, you know, we can do everything. But I don't know. So the technology there is much less developed than optics. And again, on this terahertz theme, with vial semi-metals, you might be able to make topological amplifiers for terahertz light. I'm going to concentrate on this topic. So this is done with Frederick Nathan and Ivar Martin. I'm pretty excited about this as a new paradigm for light amplification using topological principles in a way that's orthogonal to the commonly used methods nowadays for amplifying light, which rely on nonlinear crystals. So this will be the main topic. So in the next part of the talk, I will concentrate on this example of capitalizing on topological physics to produce new ideas for amplifiers. So I would say, ask me anything that comes up. As it comes up, I'm happy for interruptions. Let's start. So what do we need to talk about with topological amplifiers? So we need to talk a little bit about the underlying theory, synthetic dimensions for multiple Floquet drives. Then I'll show you how I can get, in a zero-dimensional system, a Chern insulator, a two-dimensional Chern insulator, and topological frequency conversion and amplification. Once we have that, we can ask, can we actually apply these principles to real material, and in particular, vial semi-metals? And I'll show you that the answer is almost. If the material has sufficiently good properties, then we could do that. Okay, so any questions so far? That's a good question. So I think, you know, coming from the background, thinking about quantum Hall effect, et cetera, there was a lot of surface acoustic wave interrogation of quantum Hall states, right? Terahertz is the right scale for Mott insulators physics. So you can imagine using something like that for probing materials. Yeah, you can use light. So. Yeah, I mean, we're working on the marketing still, Chiron. No, but I think, yeah, the same way that, yeah, part of the motivation was you can use it to probe other properties of correlated materials, but I was telling Eugene yesterday, so I was surprised to find out what the main application of carbon dioxide lasers, CO2 lasers. You know what the main application of CO2 lasers is? Wrinkle elimination. Cosmetics. Oh. Wrinkle elimination. We couldn't predict that.
How sugar content is. One of my talks.
All right, looking forward to that. Okay, so other questions? All right, so let's do some physics. So let's think about a system like a spin half that's periodically driven, but in the slow drive regime. So the drive is stronger than the frequency. Usually people talk about Floquet. I don't want to talk about Floquet. I just want to say, let's think about the dynamics of such a driven system. We can expand the wave function in harmonics of the drive. Still have the harmonics depend on time. This is an arbitrary expansion. It's not unique, but it's legal. And if you stick this ansatz into Schrödinger equation, time-dependent Schrödinger equation, you get something like this. What is this? Time-dependent Schrödinger equation for a wave function of a particle on a lattice with nearest neighbor hopping, a tilt, and an on-site potential. what's this nearest neighbor hopping? This is absorbing or emitting a photon from the drive. The tilt, photons have energy. So when you emit a photon or you receive a photon, the energy of the system has to accommodate that. There's conservation of energy. And what we see is this gives rise to something that looks like another dimension in the problem. We start with a 0-dimensional system. We have a 1-dimensional system with the caveat that it's on a slope. So if the frequency is sufficiently small, that slope is sufficiently shallow, the system can actually explore a big chunk of this 1 dimension. Can we do this in more dimensions? How about we put 2 drives? Small frequency, maybe incommensurate. Again, you can make the same ansatz of expanding in harmonics. Stick this equation into time-dependent Schrodinger equation. It takes more than 1 slide. I'm not going to show you that equation, but the upshot is that the behavior of this wave function is as of a particle that can move in 2 dimensions, n1 and n2, under the influence of a force that looks like this omega vector, omega 1 in the n1 direction, omega 2 in the n2 direction. That takes care of conservation of energy. And in fact, thinking about conservation of energy is a good thing, even though this system is driven. And because of conservation of energy, the system is confined to a strip, this red strip, and can move perpendicular to this omega direction. The thickness of the strip is the bandwidth of this Hamiltonian. If you take in a photon, or you give it out, so if you take in too many photons, but the bandwidth is limited, there's nowhere to put this kinetic energy into. And therefore, that's not possible. So in the finite bandwidth system, thinking about conservation of energy is very good, and it leads you to this confinement into this strip in this synthetic 2-dimensional space. So this motion is restricted by energy conservation. This motion corresponds to exchanging energy between source 1 and source 2. And that's one of the main principles of this frequency converter that I'll show you. Now, this space is infinite if omega 1 and omega 2 are incommensurate. If omega 1 and omega 2 are rational to each other, then I would have to put periodicity conditions on this lattice in the same way that we think of quantization of momentum states in carbon nanotubes, for instance, that wrap around each other. Yeah.
Are there any limitations on the dimension of the 0-dimensional, like the number of states?
There's no limitation, but as you make this system have a larger bandwidth, then energy conservation would allow you more motion along the omega direction. In fact, if you think of many body systems that have an infinite bandwidth, so unbounded from above bandwidth, they can heat up. That's what heating means. It's going up in this direction. Other questions?
Yeah, the drive is by light or by photons or by...
So far it's just by fiat.
Just generic.
Yeah, just general. So there's general formalism, but light is but you should think about light. What do I want to do with this? I promised a 0-dimensional system turned into a 2-dimensional churn band. Here's how it goes. So here's a Hamiltonian, the Benevig-Hughes-Chang Hamiltonian for a churn band in 2-dimensional spin-orbit coupled material. Sigma x times px, sigma y times py, and then cosine px, cosine py times sigma z with a magnetic field. If m and b obey this relationship, there will be a Chern number 1 or minus 1 in this. How do I turn this into the system that I talked about before? Simple. Let me take px and say that it's omega 1t. Let me take py, say that it's omega 2t. In that case, I do this consistently everywhere. What I have now is a new Hamiltonian that describes a spin half that's driven by 2 circularly polarized, by 2 elliptically polarized light beams. So this. But this is a Chern band. This is, it lives over a Chern band. And so for 2-dimensional system, a Chern band means that you have a non-trivial sigma xy. You have a Hall conductance that's quantized. Here, the Hall conductance would appear as a conversion of one beam to the other. Energy from one beam will go to the other beam. So the spin will absorb energy from one of the beams, but emit it into the other beam. So one beam will be depleted, and the other beam will be amplified. I'll show you how this works. Okay, so let's remember what happens in an anomalous Hall band. So we know what motion with a magnetic field is. You know, the dp dt is B cross V. Electron is negative in this to get the signs right, but signs are not our forte today. And then you can ask, what about motion with Berry curvature? It's pretty much the same, but dual. The velocity is given as the group velocity plus a Berry curvature cross with the force. And what is this Berry curvature? We define a Berry connection as the gradient of momentum of the wave function. Berry curvature is the curl of this vector potential, but it's all in momentum space rather than in real space. This good? So I PowerPoint simulated this kind of a band. So here's a two-dimensional band structure, but not the band structure, but rather the Berry curvature as a function of momentum concentrated around the gamma point of this band. And let's think about what happens when we take a particle and apply a force to the right in such a band. So in the momentum space, the particle can only go according to the force. dp dt is the force, so it'll just go to the right. In real space, we'll have to integrate this equation. Group velocity will give rise to Bloch oscillations back and forth in the direction of the force. This is conservation of energy. You cannot absorb energy more than your bandwidth allows, so you go back and forth. That's Bloch oscillation. But in perpendicular to the force, you can take advantage of the sigma xy of the band. The Berry curvature will make the particle move in real space perpendicular to the force. So pay attention. So this is roughly how it goes. As we go from one side of the Brillouin zone to the other, and then back here, the particle will move back and forth in the direction of the force, but it can accumulate motion perpendicular. Hall effect. That's what it is. If I do it again, that's how it will go. The y component will continue to accumulate. The x component stays constant. Now we can go back and ask, what about our driven spin half? If it's like a particle in a two-dimensional Chern band, we can think of that spin half as being a particle, say, in the valence band of this Chern insulator. And now, instead of px and py, we have the phases of the two drives forcing you to move in a particular path through the Brillouin zone that will average over the entire Brillouin zone. So when the particle goes through regions of high Berry curvature, in real space, in the synthetic real space, the particle will climb up in this N1, N2 ladder. So take a look again. So here the trajectory is such that we're driven in a particular direction, but of course the Brillouin zone is periodic. So if you leave here, you turn up here, and so forth. Every time that we go through a high Berry curvature region, we climb up a little bit. It's not a simulation, it's an animation, but it's a pretty good one. Questions about this? Oh, I don't have it in this talk, but I'll answer after in the question period, okay? This order actually makes the topological aspects of this show up. And you're in a good company, because when I talked about this stuff with Pete Brower, he also asked exactly this question. Yeah, it's a better question than what happens when it's in the magnetic field. Yeah, so this, so the motion along this direction becomes the average Berry curvature cross the force, right? But what does it mean? So this motion in N1 and N2 space up means that we give up N1 photons and absorb N2 photons. Omega 1 photons and omega 2 photons. This is not one photon becomes another photon. This is in the limit of strong drive where the quantization of photons is not good. So it conserves energy and not photon number. Now, so that means that the spin is doing work on one of the drives and taking work from the other. The power that's associated with this work for dE1 dt, the energy coming from source 1 is omega 1 times dN1 dt. dN1 dt is just Berry curvature cross omega, so it's omega 2 times the Berry curvature. And likewise, for dE2 dt is omega 2 times dN2 dt. No matter what you do, you end up with the conclusion that on average, you'll get a power that's Chern number times omega 1, omega 2, going from one drive to the other. This is what we call topological frequency conversion. Questions? This is not super practical, but you can do this with a spin-half. You can do it with a classical magnet. This effect is totally classical, even though we understand it from the perspective of topological bands. But it's really classical. So it's a classical effect on spins that you can see. Okay, so now we showed how to do topological frequency conversion. You can think about it as an amplifier in the sense that maybe there's a beam that you know how to produce well, and maybe there's a frequency that you want to produce, but you don't have machinery to do that, to do it. And so you can use a magnetic system to do this conversion. Of course, you need to choose what wave you're dumping the energy into. You can do this either in terms of a seed beam or by embedding your magnetic system in a cavity that chooses that frequency for you. You need time reversal symmetry breaking for this. That's possible. Another comment is that this effect is classical. However, even if your seed beam is a single photon, you can produce this. So this also works in the quantum regime of weak drives. All right, so now the question that I wanted to ask, can you use this, can you apply this principle to a material, to a bulk material? So for instance, the Hamiltonian that we want to think about is the Pauli matrices dotted with some kind of a dotted with a vector potential of two light beams, right? When I say this, I'm kind of jumping ahead. What we have here is the vector potential. Sorry, sorry. We went to Timo Rossi yesterday, and in the usual fashion, Timo came by and gave us 2 shots of Anisado. You see the effects right now. So we'll do our share and like advertise his place. Maybe not the night before you talk. So here we have Pauli matrices dotted with a magnetic field. That's what it is, right? Magnetic field of 2 circularly polarized light beams. Magnetic fields are awfully weak. So bear that in mind. But just look at the Hamiltonian. It's really reminiscent of Weil semi-metal Hamiltonian, sigma dot p. And if you do minimal coupling, then it becomes sigma dot p minus a. A is the vector potential. The sigma dot a really means that we're coupling to the electric field. Electric field, the speed of light stronger than the magnetic field. So it's even much better. But this Hamiltonian and this Hamiltonian are sufficiently similar that we took on this idea of studying the effect in the Weil semi-metal. And here's the result. So let's think of a doubly driven Weil semi-metal, a Weil node. So we have P dot sigma, we have minimal coupling, we have a tilt as well. But with this Hamiltonian, you can see that what happens to the momentum is that it just gets shifted by the vector potential. And that makes sense, because the shift in momentum is the integral over time of the electric field, which is just the vector potential. So we know this. If the vector potential comes from 2 beams, what would be the trajectory? So think about the dispersion of such a Hamiltonian. We have a Weil node. It's tilted a little bit. We need that. Think of a Fermi surface that sits a little bit in the valence band, so the states below this ellipse are filled. And think about this ellipse as being really asymmetric relative to the Weil node. We need that. And now let's think about the 3-dimensional Brillouin zone for this material and the motion that electrons have upon double drive. Turns out, you put this in Mathematica and plot it, turns out that that motion makes a bagel. And it's kind of a funny bagel. It's a bagel that reverses on itself halfway. So if you think about like sesame bagels, as I often do, it's like one half has the sesame on the outside, the other half has the sesame on the inside. And I have a picture of the continuum, the continuum version of that in a second. So this is what 2 drives do. And of course, look out for whether the Weil node ends up in the inside or the outside of this bagel. That will be the topological content. Okay, so the semiclassical motion of the electrons in this band goes like this, based on this equation that I showed you before. There's group velocity, there's the anomalous velocity coming from the Berry curvature. The Berry curvature comes from a monopole Berry curvature at the Weil node. each electron in the vial semi-metal is like that spin that I showed you before. And it makes a tour of the Brillouin zone that depends on its initial location and then shifted by this bagel. There are many electrons. Each one will have a different trajectory. And the trajectories will differ in where the vial node is. But bearing that in mind, let's see what the work that such motion will give. So the power done by field 1 would be the field dotted with the velocity of the electron. But the velocity has this component over here. And that will result in a power that looks like the field 1 cross with the field of source 2 times the Berry curvature. Now, if you average it on the entire trajectory, then you end up with this form. Instead of differentiating with time, you can differentiate with respect to the phase of the drive. Phase drive 1, phase drive 2, the Berry curvature. But hang on a sec. A1 and A2 are just the momentum, right? The momentum shift. So this is really the TKNN number of this trajectory relative to this monopole. Here's the continuum version of this trajectory. So you see this bagel that wraps on itself. And this will give you 1 if the vial node is on one side, minus 1 if the vial node is on the other side. So it's the Chern number of this trajectory with respect to the vial node times omega 1, omega 2 over 2 pi for each electron. So far, so good? Yeah, we took some regular Brillouin zone. But we didn't, sorry, the Brillouin zone didn't come up here because you want to keep your field amplitude sufficiently small such that you don't explore the periodicity of the lattice, because then you'll find things that are not vial nodes. So you want to keep the amplitude of your drive such that you're in the vial regime. You integrate over the trajectory. So the electrons, they make a two-dimensional surface embedded in this 3D. And that surface is the surface of a bagel with the sesame inside, sesame outside story. Right, so you can stick numbers to this, and under optimistic assumptions, you estimate how much power this can convert, and it comes out to be ginormous. It's like a gigawatt per centimeter cubed. And the relevant ranges are terahertz frequency and 1,000,000 volts per meter fields. It's not too big. But electrons are like ants. They're not pushing in the same direction. If you're lucky, they'll average in a positive direction, but they'll cancel most of it, but they'll cancel a lot of their strength. So let me show you how that works. So there's a k-dependent pumping direction. Each k-state may have a different TKNN number. So for instance, you can have 0 Chern number, 0 TKNN number if the vial node is in the hole of the bagel. You can have 1 if the Chern number is in the top part of the bagel, and minus 1 if it's in the bottom of the bagel. Now you can ask, what happens if the vial node sits on the bagel? And the answer is bad things. Because what this bagel is indicating is where the vial node hits the trajectory, but the vial node is a gapless point. So every time that the trajectory of the electrons hits the vial node, they can get excited into the conduction band from the valence band that produces heating. So here's a conversion map. And we get the conversion direction in one direction for the top part, other direction in the bottom part of the bagel. So now I mean electrons that start the trajectory in these parts of the Brillouin zone will pump in that direction or the other. And you can see now why we need an asymmetric occupation of the Brillouin zone in order to get finite pumping. And I'm going back and forth between cuts of a 3D of the 3D dispersion shown in 2D and integration over the entire 3D system. But this is just a representation. Now, there are those circles around the bagel. Those corresponds to when the vial node sits on the side of the bagel. I call them the ring of fire. This is where heating comes from. Every time that an electron goes to the vial node, it has a good chance of being excited. And then when it decays down, it produces heating. So taking all that information, we can construct a Boltzmann, we can construct a simulation of this in terms of a Boltzmann equation of the driven electrons, not taking into account interactions between electrons, but taking everything else into account. And we can get a conversion map for the particular filling that we have of the vial semimetal. And here it is. So there's a conversion region that's strong. So remember, this is the Fermi surface, but the full side is in the big side, right? Because this is the valence band. And these are empty states. Nonetheless, you can see that there will be conversion throughout. This is because the drive is fairly strong. What?
When you take into account the Boltzmann everything,
Oh yeah, but the story was different before. So what do we take in the Boltzmann? We take, it's a simplified Boltzmann in the sense that we take a relaxation time that's the same for all processes. And we see a good conversion region, but there's also heating coming from these rings, and also heating coming from just momentum relaxation. After all, we're driving a metal. So there's spin momentum relaxation region that creates heating. There's this recombination surface, so-called ring of fire, that gives heating, and that competes against the conversion region in between. Right. Now I wanted to say that at least this ring of fire we can deal with. If instead of having a incommensurate frequency ratio, which produces a two-dimensional surface in the 3D, we can think of an harmonic combination. Omega 1 equals some P over Q omega 2. Then instead of having the surface, we get Lissajous shapes. So let's call this Lissajous regime. In this case, the ring of fire heating, which is remarkably has the same scaling as the conversion effect, gets suppressed by an extra term, which is 1 over omega times the relaxation time. So you want a relaxation time that's much larger than the frequency of the drive. No wonder. But in this Lissajous regime, only electrons that have their line trajectory going to the vial node are affected. But that's one dimension less than what we had before. That's responsible to like 2 orders of magnitude suppression of this heating. So you want to operate this device in the Lissajous regime, say, in the rational, so commensurate frequency ratios, and that's probably optimal. So with that in mind, I can show you what the calculation gives. So ideal conversion will give you this E cubed over omega effect. Now, don't be fooled by this. This is not a chi-3 effect. This is only true when the electric field is stronger than the frequency. So up to the frequency, electric field times Fermi velocity over frequency. Up to the frequency, you get 0 effect. And then once you exceed the frequency, you get this topological conversion that's proportional to E cubed. So it's a nonlinear effect. It's intrinsically nonlinear. And at high fields, it has this form. And there's a heating form that has the same scaling, but with this exponent that modifies it. If we have magic ratio between the frequencies, we can ask how much conversion power we get. So we get negative conversion power, so more heating than conversion, as long as the relaxation time is below around 1 microsecond. However, if we think about this Lissajous regime, then we start getting positive conversion power already around 250 250 picoseconds. So I said microsecond, but it's a nanosecond. So at nanosecond, you get things going for magic ratio, but for Lissajous, already at 250 picoseconds, you will start getting good conversion. And this was calculated for 2 to 3 frequency ratio. Further developments relative to this. Yeah. Yeah, you assume that they're the same kind of scale, which optimizes. Yeah, John.
But I mean, in solid state, don't all vial nodes come in pairs?
Right. So you need to break inversion or time reversal or both to get this combination, but they don't always come in pairs. They come in pairs sometimes, but only the same energy. So by controlling the chemical potential, you can actually control that. By controlling the chemical potential, you can choose which vial node you have, and you control the chemical potential with doping. Don't ask me about this order when we dope. Yeah. That said, I don't have a material. We have materials in mind, but none fulfills the requirements yet. Other questions? So, okay, so just one more minute. Further developments, we need to take into account things like plasmon resonances. If we think of having a vial grain, it's going to have an electric response. There will be a plasma frequency that's proportional to the chemical potential, but chemical potential and frequency and amplitude, they're all the same scale. Bless you. But the plasma frequency actually modifies the electric coefficient very much. It may destroy this effect, but if you tune it right, it may amplify it, because you can amplify the electric field inside the grain to bring out this nonlinear effect further. And likewise, you can think of taking one grain and put it, and then forming an array of these grains, such that you get constructive interference along the direction of the propagation of the idler mode of the seed, and destructive interference going backwards. That will choose your mode. So you can imagine a three-dimensional phase array for these grains with the thing that you want to amplify coming in this direction, and the source, the energy source, coming perpendicularly. So that would be what the device would look like. Broader questions: what kind of materials we can use? Probably cobalt tin sulfur is probably the closest, and Prinarang was advising us on materials. And there are a lot of other works on nonlinear effects in vial semimetals, so I wanted to mention them, particularly from Joel Moore's group and from Takashi Oka's group, and here Ying Gran and Ken Birch. So this fits somewhere in this space of nonlinear effects. So that's a good place to stop. So I was trying to advocate that we need to think about these new materials in the context of new devices. And I gave you a very specific example of how we can leverage topological concepts and topological materials for a new paradigm for an optical amplifier that does not have the limitations of phase matching and mode matching that nonlinear crystals, for instance, have. And with that, maybe I'll stop. Thanks again. Sorry for going a little over time.